space-time diagram on. It's a curved surface. That's all. That's all we need to do. So what we do is the time axis goes like this. This is time. The space axis, so this runs along a line of a circle of latitude, and this space is up here. The space axis runs along lines of longitude. Okay, so we've taken that space-time diagram and just drawn it on a warped surface. And now the question is, we have, say, 3 snapshots here. Here's one snapshot, here's another snapshot, here's another snapshot. In each one of those snapshots, the ladder, so this is when Alice jumps off the ladder, when she steps off of it. At that initial time, the ladder sits here. Okay, and she's just jumped off the ladder. Okay, and then at some later time, some later snapshot, the ladder is here. The ladder is parallel to lines of longitude. Okay, and Alice is sitting at the bottom of the ladder like that. And the point here is, we go back to these diagrams, what Einstein wants is Alice's trajectory to not be curved, but to be straight. That's it. So Alice has to get from this point, this initial snapshot where she's just stepped off the ladder, to this snapshot where she's at the bottom of the ladder, curtain. We need to connect those 2 dots with a straight line. That's all we have to do. How do we make a straight line? What's the definition of a straight line? We talked about this at the beginning. Shortest distance between 2 points. How would you do that? Well, you would do this. You would think of this. So this is our surface that we're drawing it on. Okay, and what we do is, so you can take like a felt marker and draw, the first ladder, the ladder at the initial time, the ladder at a middle time, and the ladder when she hits the ground, as our 3 snapshots, and then just point out, well, Alice needs to get from here to here on a straight line, along a straight line. How do we make a straight line?
You can draw that on that wall with a white
Yeah,
pen.
you can draw that, absolutely. So you can draw with an erasable marker or whatever and do that. So all you do is you just take a string like this, you put one end of the string on one point, one at the other point, and what am I going to do to make a straight line? Pull it tight. Okay, there, that's it. And then you can take out your marker and get a student to help and just draw that line, connecting those 2 points. We've made a straight line now. Alice is getting from the top of the ladder to the bottom of the ladder along a straight line in space-time. Okay, very simple. So there it is. So we've done that. And in terms of our picture, it's this guy here. It's the path that a plane would take from New York to Paris, moving on the curved surface of the Earth. If I were to extend that to a full circle, it would be a great circle, like that. Okay, so this is now straight, just like Einstein wanted. Okay, now Bob stays at the bottom of the ladder. In the first snapshot he's here, in the second snapshot he's here, in the third snapshot he's here. We connect these dots like this. This is Bob's trajectory. Question, is that straight or curved?
Both. It's on the ball.
How would I test? But by straight line I mean shortest path or shortest distance.
Yes.
Is this here the path or shortest distance from there to there?
Yes.
Was this the path an airplane would take to fly from there to there?
No.
No.
How can I test it?
On the ball.
On the ball. Okay, so thank you, Dennis. So now we've got those 2 points, the beginning and ending point, okay, which are, say, here. They lie along a circle of latitude. Is that going along latitude?
No.
Okay. Okay, so there it is. How do we test if this is a straight line? Pull it tight, boom. See that? And you can do this more dramatically, like putting it a little bit further apart. This is not a straight line. I pull tight, that's a straight line. That's the path of shortest distance. This is not. Okay? The key point here is that, so Bob's line is actually curved. Just like Einstein wanted. In which direction is it curved?
In space direction.
Up or down? Yeah.
Upwards in the space direction.
Right. How many say down? How many say up? So the way to do this, I'm sorry, Dennis, can we do that just once more?
It's curved down.
Come on, man.
Yeah.
There is no up or down. It's just curved.
It's probably curved.
Okay, so
Down because
So Bob's trajectory was this one over here, right, along a circle of latitude. So what we do is we simply take Bob's starting point, we stretch this thing tight, and we see that in order to have, this is now a straight line. No matter where I move my left hand, I've got a straight line connecting this point to my left hand point. These are all straight lines. Okay, and I make that straight line. I make it so that his trajectory initially matches Bob's. So Bob's is the one going along a circle of latitude. The straight line starting at his point goes down. Do you see that?
I can see it down quite a lot.
Okay. This whole, every single line
The
is a straight
second
line
point,
here.
Oh, okay.
If I make it so that this straight line matches Bob's initial trajectory, which is horizontally, then that straight line bends below. But that's the straight line. It's actually Bob's that bends above this. Is that clear?
Mhm.
So I'm sorry we don't have a lot of time to elaborate on that, but it's just simple demos like that. And so at the end of the day, what you show to the students is that this is a straight line here. This one, if I were to continue, would be a great circle dividing the sphere in half. This is straight. This thing bends above that. It's like saying this, and Bob's trajectory is doing that. Bob is in fact curving up. Bob is doing this. Bob is in fact moving faster and faster and faster in the upper direction all the time, without going anywhere. Okay? So, but let me clarify that point. What Einstein said, what Einstein realized is this. This apple is not accelerating. This apple is doing absolutely nothing when it's in free fall. Okay? When it's in free fall like this, there are no forces acting on it. There's no acceleration. It should be a straight line trajectory. This is identical to being out in the middle of empty space. Okay? If I take Alice and the apple, and Alice is, say floating out in the middle of empty space, if she holds onto the apple and lets go of it, just releases it, what's going to happen? It's going to stay right in front of her face. Okay, now here we are on the earth. She steps off the ladder and she's free falling like this, and she releases, as she's falling, she releases the apple from her hand. What's it going to do? It's going to stay right in front of her face. Because according to Galileo, that we've known for 300 years, everything falls at the same rate. Okay, so the point is this. This situation of the apple floating in front of her face, this situation not only seems like Alice floating out in the middle of empty space nowhere, it not only seems to be the same, it is the same. Seeming and is. This is a very powerful lesson in science. Sometimes things seem to be the same, and if you think a little bit about it, and you're a little bit clever, you will see how, in fact, they are the same. Okay, so the point is that just like the apple floating out in the middle of empty space, that's at rest. That's the thing that you measure motion relative to. Okay, now go back to the earth, the apple falling here on the earth. This is the thing that's at rest. This is the thing that you measure motion relative to. What is Alice's motion relative to this thing that's at rest? Zero. It's at rest. She's just floating. She has a straight space-time trajectory. Okay? What is Bob's motion relative to this apple? Accelerating up. Moving faster and faster and faster up. He really is accelerating. We really are, standing here right now, are moving faster and faster and faster up. We are accelerating up. Relative to what? Remember, all motion is relative. Okay, relative to what? Relative to the thing that is at rest, which is the apple falling. Relative to a falling apple, we are indeed accelerating up and up and up. And that's what this trajectory is. This is the trajectory of a falling apple. Okay, so here's Bob standing there, and here's the apple. Okay? We've just taken a snapshot, and we've shown Bob, and we've shown the apple. This is a straight line. This is at rest. This is not. This is curved up. It's continually accelerating up. Okay, so the ultimate lesson here is that gravity is not a force. Okay, gravity is the ground accelerating up. Forever. Eternally. How is that possible? Through the magic of warped space-time. This is a huge paradigm shift. Think about that. We are literally accelerating up right now, all the time, continuously. That's a big difference. And now you might wonder, and we have to quit, but let me just say this one last thing, because this is the crucial point. Was Einstein right? How do we know? So far, we've been claiming that artificial gravity and real gravity, actual gravity are similar, et cetera, et cetera. And so why